Last week we talked about what a rate of reaction is, and we talked about rate laws and the order of different reactions. So we were looking there at the rate of the reaction and how it's related to the concentration of a reactant. So an integrated rate law gives us the relationship between concentration and time. And that's a lot more useful because the actual rate at any given point is like, whatever. But we would like to be able to predict what the concentration is at any given point in time. So this integrated rate law, just like the regular rate law, is going to depend on the order of the reaction. So we'll look at first order integrated rate law first. So if we have a simple decomposition where A is decomposing to form products, here is our rate law. So the rate is equal to a rate constant times the concentration. The rate is also equal to negative delta A over delta T. This is the definition of rate that we learned on day one, right? So here you would take the coefficient, 1 over the coefficient, 1 over 1, it's not written. For a reactant, you have a negative, and then it's the change in concentration over the change in time. So if the rate equals this and the rate equals that, then these two things have to be equal, right? So negative delta A over delta T must equal K times the concentration of A. This is called the differential rate law, and here integrated and differential, those are terms that are used in calculus. And these are directly related to calculus. The good news is you don't need to know any calculus to be really good at this stuff. So instead of messing around, we just say, well, after integrating this, here's what we get. So this is the integrated rate law, and if you're not into calculus, just believe it, and you'll be fine. So this is saying that the natural log of the concentration at time t is equal to negative the rate constant times that time plus the natural log of the concentration initially at 0. Okay. When we have this, we can graph the natural log of A versus time. And in this first one, it's set up in linear. So y is equal to mx plus b. So on the y-axis, we have the natural log of A. On the x-axis, we have time. So t here is our x variable. The slope then is equal to negative k. This is a negative slope, and the rate constant has to be positive. But the rate constant is equal to negative of the slope, right? Negative k equals m, which means that m equals, k. K equals negative m. So we do end up with a positive rate constant. Any questions yet? So let's see how we can use a graph like this. So we're going to look at the decomposition of SO2Cl2, forms a couple of products. So they monitored the composition of the reactant at a fixed temperature as a function of time. So the fixed temperature thing is important because reaction rates are going to be different at different temperatures. So we always try to just change one thing at a time so that we can study that. So here we're measuring the time. At different times, we're measuring this concentration. And so you see they started at 0 and went all the way up to 1,500 seconds. So Our task is to show that the reaction is first order and determine the rate constant. So how could we do that? Well, just with our knowledge that we had until today, what we did to determine the order was we would have to look at the rate of the reaction and see how it changed with concentration. And this is not set up that way, is it? This is a different type of experiment. So what we can do here is we can graph this data. We're going to take the natural log of the concentration, and we're going to put that on the y-axis, and we're going to put time on the x-axis. Now, if you have forgotten all of your graphing skills, please come and talk to me, and I'll bring you up to speed, because we're going to have a lot of graphs and a lot of equations for lines, and we need to be able to deal with them. So if we graph that data, poof, magic, we get this result. So the graph of natural log of A versus time gives us a straight line. So that tells us that this is a first order reaction. Because if you graph zero order or second order data, it won't be a straight line. So because it's linear, this is a first order reaction. So that was one of the things we're supposed to do. Let's find the rate constant. So the equation, the integrated rate law for first order is the natural log of the concentration at time t is equal to negative k times t plus the natural log of the concentration of A at time 0. And you may feel like, oh my goodness, here's an equation. I don't know that I'm going to be able to remember this. If you look at the last page in your lab manual, you don't need to get it out right now. It says useful information for Chem 1B exams on one side, and there's a bunch of equations, and on the other side is a periodic table. Which maybe should have been oriented the other way, but whatever. The integrated rate law equations are on here. They're not identified, but they are in order of 0, 1, 2, and so it should be pretty easy to figure it out, because I sometimes have a hard time remembering these as well. So here we have the equation for the line. So we're going to learn how to do this in lab today if you're not familiar with it. We're going to graph some numbers in Excel, and Excel can draw a best fit line and give us the equation for that line. So this just pops up from the computer. Once you get the hang of it, it's super easy. So here, this is the slope. Well, this is the slope term in that equation, right? So negative k is equal to the slope of the line, negative 0.000290. Any questions about that? I mean, it actually is just that easy. You look at the slope, and you multiply both sides by -1, and that's your rate constant. What are the units of the rate constant? Yeah. Let's see. So, personally, I just don't remember the units on the rate constants because I can figure them out. So we can figure it out like we did last week. For a first order reaction, the rate is equal to the rate constant times the concentration. And then we plug in the units. The rate is measured in molarity per second. and the concentration is in molarity, and then we have K. So if we simplify that, we end up with K having units of 1/2, or s to the minus 1. Kind of messing with you because last week we talked about zero order first, and zero order is molarity per second. But this one is just per second. So rate constant equals 0.000290 s to the minus 1. Any questions? Let's see if I did it right. Yep. Okay, here's another problem. Use the graph in the best fitting line to predict the concentration of SO2Cl2 at 1900 seconds. Well, if we look at this graph, we see that it only goes up to 1500 seconds, right? So the line doesn't actually go that far, so we can't just, pick a point on the line. We can't just read it off the graph. Reading it off the graph is not very accurate anyway because, it's like there's not any great division lines there. It's just kind of iffy. What we want to do is we want to use the equation for the line. So y is the natural log of the concentration and t is time. Well, we know what time, right? We're looking for 1900 seconds. And so we'll put that into our equation. Well, let's just write it this way. So, that's going to be confusing. So y is the natural log of a at time t, and that's equal to this number here. The rest of this we can just use straight out of here. I'm just re-identifying y so that we don't find y and think that that's the answer. So we have negative 0.000290 times 1900 seconds minus, I didn't plan that out very well, 2.03. So here we have the variable on the left side and all the numbers on the right side, and so we can just solve this. Negative 0.000290 times 1900 minus 2.3. So this gives us negative 2.851. There's no digits after that. That's the natural log of the concentration. Okay? How do we find out what the concentration is? Natural log is a function, right? So we can't just divide by it. We have to do the opposite. What's the antilog? E to the x. So if we take e to the natural log of at, that's the same as the concentration of A. And then on the other side, we have e to the negative 2.851. So your calculator has a button for that. And we press that, and we find that the concentration is 0.057786505. That's all the digits my calculator is showing me. Sig fig rules aren't super helpful here because we've got natural logarithms, and so it's like, I don't know. So what I would do is write down plenty of digits and then just use the other numbers that were given and get a ballpark correct number of sig figs, okay? So this has 3 and that has 3, so let's do our concentration to 3 sig figs. And what's the unit on concentration? Molarity. Is that a reasonable concentration? Well, it's not negative. That's good. Negative concentration is impossible, right? This is the natural log of the concentration at time 0. So we could find the concentration at time 0. That would be e to the negative 2.3. And that's equal to 0.1. And at 1900 seconds, the concentration has to be lower than it was to start with, right? Any questions? So here's a question for you. If you're awake, nod your head up and down. You awake? Do it. Nod your head up and down. It's okay. Everybody's awake? Well, people aren't nodding their heads, so I guess they're not awake. Okay, that's the correct answer. 2 for 2 today. Another practice question. Cyclopropane rearranges to form propene in the gas phase. The reaction is first order in cyclopropane. That's going to be useful. It's first order. And has a measured rate constant of 3.36 times 10 to the minus 5 per second at 720 Kelvin. So 720 Kelvin is in there. Does that mean that we're going to need it in our calculation? No. This is just saying this is the temperature at which we did this reaction, so that, you know, if you're really into all of this stuff and you wanted to duplicate it or something, that's the temperature you need. But we don't actually need to know what that is. If the initial cyclopropane concentration is this, so that's the initial concentration, what will be the concentration after 235 minutes? Well, this is a first order reaction. And we're dealing with concentration and with time, and so we want to use the integrated rate law. The natural log of the concentration of A. And this is cyclopropane. Do we care right now what the formula for cyclopropane is? No, we don't. We just need the concentration of something. A is easier to write. So A just represents the concentration of cyclopropane. So that is going to be equal to negative K times the time plus the natural log of the concentration at time 0. Okay, well, let's start plugging things in here. We're told what the rate constant is. So negative rate constant, 3.36 times 10 to the minus 5. It's always a good habit to write all the units in. Here it doesn't really help us out that much, but a little bit. And what's the time? Well, it's 235 minutes. If I put minutes here, is that going to cancel with seconds? No. I need to convert minutes to seconds. Right? So I want minutes in the denominator, so those cancel out, and I want seconds in the numerator. How many seconds in a minute? 60. So that's something I'm going to assume you know. 235 times 60. 14100 seconds. So plug that in here, 14100 seconds. We see that those seconds are going to cancel out. Plus the natural log of the concentration at time 0. So time 0 is the initial condition, and this is the concentration. 0.0445 molar. Well, so this is convenient. Again, all the numbers ended up on one side, so we can just calculate what that is. So if you haven't already, get your calculator out and make sure that it's functioning the way it should be. I mean, we know that when the calculator screws up, it's actually us. We're making the mistake. But we're going to pretend that it's the calculator that's making this mistake. So if your calculator is misbehaving and won't give you the correct answer, let me know and I'll come over and have a word with it. Okay, so negative 3.36. If you did not get comfortable with the scientific notation button on your calculator in Chem 1A, you need to do it now. Do not do times 10 raised to the minus 5. There is a special button on your calculator, EE or EXP, and everything will go much more smoothly if you learn how to do that. So I'm typing in 3.36. I'm pressing the EE button, which stands for times 10 to the and then I put in negative 5. And then that is times 14100 plus the natural log of 0.0445. Enter. I'm kind of looking at the numbers I have. We'll see that 3 sig figs is really common in 1B. And so I'm going to write down 5, just so I have some extras. So that's equal to the natural log of A at 1900 seconds. Does anyone have a calculator that needs to be spoken harshly to? Did it cooperate and give you that answer? I'll give you a second. So the concentration here is what we're looking for, but again, we have the natural log of it. So we're going to do the same thing we did before. We're going to take e to the power of each side. So e to the x is anti-natural log. And so natural log and anti-natural log cancel each other out, just like matter and antimatter. So a at time t equals e to the negative 3.5860. I still have that number in my calculator with even more digits, so I'm just going to use that. I'm going to press E, and I'm going to just go up and select that number and press enter to bring it in, and enter again. There's 3 sig figs, and let's write at least 2 more. So our answer then is 0.0277 molar. That is the concentration of cyclopropane at 235 minutes. Any questions? Our lectures are going to have some of these long pauses in them because I want you to actually do the calculation with me, okay? Did we get it right? Yes. I should keep track. I'm 3 for 3. Okay, so that was first order. We had 2 other orders. We'll talk about second order, and then we'll get back to zero order. So here we have a simple decomposition of A going to products that is second order. So the rate of the reaction is equal to a rate constant times the concentration of that reactant squared. Learned that last week. We also learned that the rate is equal to negative 1 over the coefficient is 1, times the change in concentration of A divided by the change in time. So like we did with the first order one, we're going to take these 2 pieces and make them equal to each other, and we get this negative delta A over delta T equals K times A squared. That's the differential law. Voodoo calculus. Ta-da! Here is the integrated rate law. So 1 over the concentration of A at time t is equal to the rate constant times t plus 1 over the concentration at time 0. These have been put into the form of a line because we're going to graph the data and we're going to use the line, and so that's why these are 1 over. It might look kind of funny. But again, this is a form of y equals mx plus b. So on the x-axis, I'm graphing 1 over the concentration of A at that given time. My rate constant is the slope, and my y-intercept is 1 over the initial concentration. Again, we're going to get a straight line if we graph it correctly. So we plot inverse of the reactant concentration versus time, and we get a linear graph with a slope of k. Any questions? Well, we're going to use graphical analysis again to solve this problem. Consider the equation for the decomposition of NO2. Concentration of NO2 is monitored at a fixed temperature. See, this time they didn't bother telling us what it was because we don't need to know. It's monitored as a function of time during the decomposition reaction, and the data is tabulated. They just took all the numbers and they put them in a table. Show by graphical analysis that the reaction is not first order and that it is second order. Determine the rate constant for the reaction. Well, this is not something I can do in lecture. We need Excel to do this for us. So ta-da, there it is. So if the reaction was first order, then graphing the natural log of NO2 versus time should give us a straight line. So here is the actual data in the black dots, and this is the best fit line that the computer comes up with. And you're like, well, it kind of goes along there, but it's higher at the beginning and higher at the end and lower in the middle. This is a curve, okay? It is not linear. So if we graph 1 over the concentration versus time, here's our data, and we do get a nice straight line. So this is how we can show that it's second order and not first order. The second order graph is much more linear than the first order graph. Any questions? And there's something called a correlation coefficient that the computer will give you, R squared. And R squared is a measure of how closely the line fits the data. How straight is this data? So if R squared equals 1, that's a perfectly straight line. Does that happen in our data? Not so much. On the day when that happens, you go buy a lottery ticket because you got really lucky. It's a lot more common to have R squareds of like 0.999 something or 0.95 or something If you get less than 0.9, that's not a line, unless you just got really, really messy data. Then you should just try doing it again. Okay, so any questions about that? We determine its second order by graphing the data. Okay, let's show by graphical analysis the reaction is not first order and that it is second order. Okay, so we're supposed to find the rate constant. How do we do that? Well, here we have the linear equation, and that matches the second order integrated rate law, which is 1 over the concentration of A at time t is equal to the rate constant times time plus 1 over the concentration at time 0. And again, that's on the page of useful information for exams, last page of your lab manual. So you just need to be able to pick it out of the list. You don't have to remember it. So if this is the integrated rate law, and that's the equation for the line, what's K? 0.255 is the slope. So the rate constant is equal to 0.255. What are the units? On this graph, because it's got natural log in it, we can't look at the graph and figure out what the units are. Here we could, although it's still a bit confusing. The units on Y are 1 over molarity, and the units on X are seconds. And so if we simplify that fraction, we've got 1 over molarity times second, or m to the minus 1, s to the minus 1. You can also find those units by plugging units into the second order rate law and seeing what you need. Any questions? You have to remember that number. Oh, actually, I can copy it. Let's do that. Oh, it's here. Use the graph in the best fitting line to predict the concentration of NO2 at 2,000 seconds. And again, 2,000 seconds is way off of this graph. Instead of making the graph bigger and extending the line, we're just going to use the equation for the line. So when x is 2,000, what is the value of y? Well, it's, oops, not what I meant to do. We're looking at 1 over a to the t is equal to kt plus 1 over a0. So t equals 2,000 seconds. That's what we're asked to find. So 1 over the concentration of A at time t equals the rate constant, or we can just look at this as the rest of the equation. 0.255 times 2,000 seconds. Oh, what the heck, let's put the units in there. Plus 100. So that's the y-intercept. What are the units of y at that point? Y is 1 over the molarity, right? So the unit then is 1 over molarity. I will not be trying to trick you with the units here, but I just want to show those of you who are interested that they do work out very nicely. So our seconds cancel the reciprocal seconds. And we have 1 over molarity plus 1 over molarity. We can add these numbers together. So 1 over A equals those numbers added together, which would be 100.255. No. Like, this looks really weird. I forgot to multiply by 2,000. We'll blame that on Monday. 0.255 times 2,000 plus 100. That looks a little better. So 610, that's all the digits the calculator gives me. And the unit's m to the minus 1. In 1A, you probably saw some equations where we end up with 1 over what we're trying to find. And sometimes students are just like, well, it's just equal. Well, no, it's not. 1 over this is equal to that. That means that this is 1 over that, right? Or use the solver. You can use a solver on the 36X Pro for this whole thing. So much less thinking. To get this into the numerator, I'm going to raise both sides by -1. Basically, I'm upside downing it, right? So a to the t is equal to 1 over 610. And this says 0.0016393 molarity. And again, a reasonable number of sig figs would be 3. So we'll say 0.00164. Yay, I got it right. This is just the number in scientific notation. I often get asked, well, when do we need to use scientific notation? We always need to be able to understand scientific notation. We need to be able to look at this and compare it to that and recognize that's the same number. My rule of thumb is if there's more than 3 zeros at the beginning, then I start to find the zeros hard to count. I have to get my finger out and count them, and that makes me feel like an idiot, right? So if there's more than 3 zeros at the beginning, I would recommend scientific notation. If you have a number like this, where you've got more than 3 zeros at the end, scientific notation is probably going to be good, okay? Any questions? So that was first order, second order. Let's get to 0. So we're going to do the same thing we did with the other ones. The rate of a 0 order reaction is equal to the rate constant times the concentration to the 0 power, which is just the rate constant. And the rate is equal to negative delta A over delta T. So we set those two things equal to each other. That's our differential rate law. We integrate that. You don't need to understand what that means. It's just like, okay, magic is done, and we get this. So the concentration of A at time t is equal to negative kT plus A0. And again, we get the equation for a line. These equations were arranged in the way that they are so that they will give us a straight line. So the plot of concentration versus time is linear. Concentration versus time, linear, and the slope here is negative, and the slope is equal to negative k. So -1 times the rate constant. Okay, so now we're going to talk about half-life. You may remember half-life from Chem 3A talking about radioactive things, and radioactive decay is a zero-order reaction, and so it follows the integrated rate law for zero-order reaction. So we can talk about the half-life. The half-life, or T1 half, is the time needed for the concentration of that reactant to fall to 1/2 of its initial value. So after 1 half-life, the concentration is cut in half. What happens after 2 half-lives? Is it all gone? No, it's halved again. So 1 half-life, cut it in half. Second half-life, cut it in half again, right? So now it's 1/4. So it keeps getting smaller and smaller, but that isn't linear. So if the initial concentration is 0.5 molar and T1 half is 50 seconds, what's the concentration after 50 seconds? 1 half-life, right? So we'll divide this by 2, and we'll get 0.25. And after 100 seconds, that's 2 half-lives, right? So we'll take this one and divide by 2 again. And get 0.125. And that's a lot of what we did in Chem 3A, is we just like, well, it's this many half-lives, and so you divide by 2 that many times. The half-life expression is going to look different for different reaction orders, although this part is the same. So for that first order reaction, the integrated rate law, here we've taken the linear form and rearranged it to suit our purposes, right? So we rearrange that equation and we come up with the natural log of the concentration at time t divided by the concentration at time 0 is equal to negative rate constant times t. Well, at t is equal to T1 half, we know that that concentration is half of what it was originally. We don't know what the concentration was, but at a half-life, we know that the concentration is 1/2. So we can plug that in here, natural log. So if the concentration at time t is 1/2 of the concentration at time 0, and that is equal to negative kT. Well, now we only have a 0 here, and those are going to cancel out. So the negative kT is equal to the natural log of 1/2. Well, what is that number? E to the 1/2. That equals 1.6487. Well, that's not a very memorable number, is it? The time here, I should really label, is T1 half. So we could solve that for T1 half. So the half-life is equal to the natural log of 1/2 divided by k, and we're going to have a negative sign. Well, the natural log of 1/2 is equal to the natural log. I'm blanking on my log skills right now. I believe it's natural log of 1 minus the natural log of 2. Nope. Not right. This is what happens when you don't teach the class for a year and a half. So we've got this. It doesn't match up with what's shown on our sheet. Because here we have T1 half is 0.693 over K. I figured it out. The natural log of 1/2 does not equal this. How many of you saw that on your calculator, but just didn't want to say anything? You trust me. Okay, don't trust me that much. That's wrong. 0.693. I am a human being, and I make mistakes all the time. And you will also make mistakes all the time. And what's important is to recognize when you make a mistake. As I go to the next slide, and it's like, oh, okay, this isn't matching. What's wrong? And then you just own it, right? I screwed up. Let's see. Did that, and now we're here. And I screwed up again because the natural log of 1/2 is negative 0.693. If you want to watch the lecture videos, I recommend watching the Tuesday and Thursday ones. Tomorrow's going to be better. Okay, I finally got there. So for first order reactions, the half-life is independent of the initial concentration. It just doesn't matter how much there was to start with, the half-life is always the same. So that constant half-life is unique to first order reactions. 0 and second order, the half-life will change. Any questions? Okay, so here we have some pictures. These are showing the first order reaction A to B at various times. Black circles are A, red circles are B. What's the half-life? I'm going to start by counting these dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 of A to start with. What should be true at the half-life? I should have half as many. I should have 5, right? So I should have 5 black ones and 5 red ones. So which time has that? 90 seconds. So if you look at this one, we've got 5 and 5. So the half-life must be 90 seconds. Any questions? So in this class, there will be some hard questions, and then there'll be some questions that seem so simple that it couldn't be that easy, and that will actually be harder than the hard questions because you'll mess with yourself and you'll overthink it. Did you have a question?
Oh, no, I was letting you know that we can't see the color.
Oh, yeah, good point. So on the black and white printout, you can't see the colors because it's black and white. So now, if you're into colored pens or something, this would be a good time to go in there and color some of them or circle some of them to see what they are. Thanks for pointing that out. 90 seconds. Okay. First order reaction has a half-life of 25 minutes. If the initial concentration is 0.3 molar, what's the concentration of B after 50 minutes? Do not use a calculator to solve this problem. How many half-lives is 50 minutes? 2. So the first half-life concentration is in half. Second half-life, it cuts in half again. So what's half of 0.3? 0.15. And what's half of that? I'm going to need my calculator. We can do it. What did I do? I fell into the trap of the problem. I'm looking at A. A is equal to this, and A is equal to this. What's the question asking for? It's asking for B. Okay, this is a common trick in Chem 1B questions. So that's why multiple choice sometimes can be helpful, because we realize, oh crap, that's the wrong answer. Unfortunately for you on the exams, I would know that that's a common mistake, and so I would put it as one of the choices. Yeah. Okay, so if that is the amount of A, then what's the amount of B? How much A has disappeared? We started with 0.3, and then we're subtracting 0.075. That's going to be B. I'm like, what? No calculator? Well, we could think of it this way. Well, can we? Yeah, it doesn't really help. After one half-life, half of it's gone to B, so B is equal to 0.150. And after the second half-life, we're going to add another half of that. So 0.510 plus half of 0.510. I don't think that helps at all. That was a nice mess. Any questions? I'll never say don't use your calculator on an exam. Here's another one. First order reaction has a half-life of 26.4 seconds. How long does it take for the concentration of the reactant in the reaction to fall to 1/8 of its initial value? We can do this using the equation, or we can do this just thinking about it. Because we have 1/8 of its initial value. So we start with 1, and after one half-life, we go to 1/2, and after 2 half-lives, we go to 1/4, and after 3 half-lives, we go to 1/8. So we have 1, 2, 3 half-lives. 3 times 26.4 seconds. let's look at how we could do it with the equation. So again, if we're going to use the equations, we'll have to use this half-life equation to calculate K, the rate constant, because we know the half-life, but that's all we know. Once we solve for K, we can put that in here, and we can make a T equal 1/8 of A0, and that just doesn't sound very fun, does it? Just dividing something in half and counting how many times you did that sounds easier. Okay. Second order. So here we have the second order integrated rate law, and again, we know when t is equal to t1/2 that a at that time is equal to 1/2 of A0. So we're going to plug that in here. So rearranging of this might be a little sketchy. So what we want to do is we want to subtract 1 over A0 from both sides. And then this is a mess over here because in order to subtract, the denominators have to be the same. Well, how can we make this have the denominator of A0? If we multiply that by 2 over 2, the fraction is the same, but then we get rid of that guy down there. Oops. So 2 over A0 minus 1 over A0 equals 1 over A0, which equals K T1/2. I will not ask you to derive these relationships. I think it's helpful to watch someone do it and say, oh, I can see how that was okay. But I'm not going to ask you to derive this. Any questions? So T1/2 is 1 over K times A0. I forgot to rearrange for T1/2. So now the half-life is depending on the initial concentration. So if we have a lower initial concentration, then we get a longer half-life. So if this concentration is small, then T1/2 is bigger. And so as A goes down, the half-life gets longer and longer. So after every half-life, it's going to take longer for it to cut in half. Zero order. So again, we take our integrated rate law, and we're going to plug in T1/2 and 1/2 A0 for AT. So we get 1/2 A0 is equal to negative KT plus A0, T1/2. It's just going to stay there fine. So we can subtract A0 from both sides, so we get 1/2 A0 minus A0 equals negative K T 1/2. And this is like 1/2 X minus 1. So it's going to be negative 1/2 A0 equals negative K T 1/2. So this time I'm going to remember to solve for T 1/2. We're going to divide both sides by negative K. T 1/2 is equal to 1 over 2K. Almost. Like, wait a minute. Did I lose my writing? I lost my writing. Dang it. Okay. Okay, we had negative 1/2 A0 was equal to negative K T 1/2. And I divided both sides by negative K, and what happened was I somehow lost the A0 in that process. A0 over 2K is equal to T 1/2. There we go. This is the only time we're going to talk about deriving these. And what I'd like to point out, why I'm even doing this, is this shows how using math and these equations, we can find new relationships that were not immediately obvious, right? Just by rearranging things, substituting stuff in. So now I get the correct one. So for a zero order reaction, the half-life also depends on the initial concentration. But as concentration gets smaller, the half-life gets smaller. So that means the half-life is shorter as the reaction proceeds. Second order, it's longer as the reaction proceeds, and for first order, it stays the same. That is a very useful table. Rate law summary table, that's got so much good stuff in it. You might want to pull up the slides from Canvas on your phone, take a screenshot. You'll get a much better result than if you take a picture of that screen. Here's the 3 orders we talked about. Here are the rate laws. We talked about that last week, and the units for K. Today we learned about the integrated rate laws. Here we have the straight line plots and the relationship between the slope and the rate constant, and here we also have the half-life expressions. We'll be using these equations a lot. And if I remember correctly, I give you all but these. The rate law, you should be able to figure that out. Okay, a decomposition reaction with a rate that is observed to slow down as the reaction proceeds has a half-life that depends on the initial concentration of the reactant. Which statement is most likely true for this reaction? Well, first of all, before we look at the choices, if the half-life, if the rate slows down, what does that mean about the half-life? Is it getting longer or shorter? Longer. If the rate is slowing down, then as as the reaction occurs, the half-life is going to get longer and longer. The time to cut the previous in half is going to take longer. Which order did that? Well, we could look at this. First order, it just doesn't matter. Here, high concentration, long half-life. So as the concentration gets smaller, the half-life gets smaller. Here, high concentration, short half-life. As this gets smaller, that gets bigger. So this must be a second order reaction. We can figure that out from what they said here. Now let's look at the choices. Plot of the natural log as a function of time is linear. The half-life increases as the initial concentration increases. A doubling of the initial concentration results in a quadrupling of the rate. You're like, ah! Well, if we didn't know that it was second order, that would be tough. So this is a second order reaction. And C says we double the concentration, we get a quadruple in the rate. The change in concentration gets squared. So that is the correct answer. This first one is a description of which order? First order. And this one? Zero order. Any questions?